In this video we're going to be looking at Le Chatelier's principle, which is a principle that we can use to predict the effect of changing certain conditions on a dynamic equilibrium system. So just to recap quickly, a dynamic equilibrium is a reversible reaction that is occurring at the same rate in both directions, forwards and backwards, and is in a closed system. Okay? So here we have an example of a dynamic equilibrium system. We have A plus B forming C. But the fact that we have this double-headed arrow shows that it is a reversible reaction. So A and B are combining to form C, but at the exact same time, exact same rate, C is breaking down into A and B. So this can only occur in a closed system. So I've just drawn a conical flask with a bung to show that there is no transfer of matter into or out of the reaction. Okay, so A and B can't escape, C can't escape, and nothing else can get in. Also, by being in a closed system, the volume is constant, which means that the pressure is therefore constant. The other bit of information you may or may not be given is the energy change, or sometimes known as the enthalpy change. So this will either be written as delta H for enthalpy or delta E for energy. They essentially represent the same thing. They show you the energy change of the forwards reaction only. So this one here has an energy change or an enthalpy change of negative 250 kilojoules per mole. And we should know that a negative energy change is an exothermic change. So that is telling us that the forwards reaction, A plus B forming C, is an exothermic reaction, which means that C breaking down into B and A must be an endothermic reaction. Now, all you need in order to predict the effect of changing concentration, temperature, pressure on the position of equilibrium, all you need is the balanced equation, the state symbols, which you will always be given. If you're given a balanced equation, you'll be given the state symbols, and the enthalpy change, or the energy change. And you don't need all of that information for all of those different changes, and I'll go through which ones you need and when. So, both reactions are occurring forwards and backwards at the exact same rate. So, at equilibrium, the concentrations of A, B, and C are constant. They won't be changing. The temperature of the reaction will be constant. It will not be increasing in temperature, it will not be decreasing in temperature. The pressure will be constant. The rate of reaction would appear to be zero, because as quickly as A and B are forming C, the C is breaking back down into A and B. So if you were looking at a dynamic equilibrium system, you would appear to see nothing happening. So, Le Chatelier's principle states that a dynamic equilibrium system will shift either forwards or backwards. They're the only things it can do, or it can stay the same. So it can either shift forwards to use up more of A and B and produce more C, or it can shift backwards and use up more C to produce more A and B. Those are the only options it has. And it will do that only to oppose any change in conditions. So if I were to increase the temperature, it would shift forwards or backwards in order to decrease it. If I were to increase the pressure, it would shift either forwards or backwards in order to decrease that pressure. If I were to add a greater concentration of A, it would shift either forwards or backwards to decrease that concentration of A. So the equilibrium, if we change the conditions, will shift either forwards or backwards in order to counteract whatever change I have made. The first condition we're going to look at is concentration. What will happen if I change concentration? So the first thing here is that energy change that we are told is not relevant. Okay? So the energy change is not needed if all you're changing is the concentration. So, in terms of changing concentration, it's reasonably simple. Let's say, for example, I've increased the concentration of A. So I've increased the concentration of A. Le Chatelier's principle states that the dynamic equilibrium will shift forwards or backwards in order to counteract my change. So if I've increased A, my dynamic equilibrium will want to decrease A. So how could it do that? It's got two choices. Either it could break down from C into A and B, or it can combine A and B to create C. Which one of those options would reduce the amount of A? It would be the forwards reaction. The forwards reaction uses up A as a reactant. If you use it up, its concentration would decrease, which would be the opposite of what I did. So, the dynamic equilibrium in this case will shift to the right. In order to reduce the concentration of A. So it's shifted to the right, it's favoured the forwards reaction because the forwards reaction would reduce the concentration of A, which is the opposite of what I did. Now let's consider perhaps I didn't increase it, let's perhaps say I decreased it. What would happen if I decreased the concentration of A? Well, Le Chatelier's principle states that the dynamic equilibrium will shift to counteract the change. So, for this example, I've decreased the concentration of A. What will happen? Well, the dynamic equilibrium will shift to increase the concentration of A. So it will do the opposite. This time, it will shift to the left-hand side. Because by shifting to the left-hand side, it can break down C to produce more A and B. If it produces more A, it will increase the concentration and it will counteract my change. So the dynamic equilibrium will shift to the left in this case in order to increase the concentration of A. So it's just doing the opposite. So to summarize, for concentration, increasing the concentration of a substance on one side of a dynamic equilibrium will favour the opposite side. So if I increased A, it would favour the other side. If I increased C, it would favour the other side. So increasing concentration of a substance on one side of a dynamic equilibrium will always favour the opposite. If I was to decrease the concentration of a substance on one side of a dynamic equilibrium, it will favour the same side. So, increasing concentration will favour the opposite side, but decreasing concentration will favour the same side. And again, if we decreased A, it would favour the left-hand side in order to replace it. So decreasing the concentration of something on the left will shift to the left. Decreasing C on the right would cause the equilibrium to shift to the right to replace C. When it comes to the effect of changing pressure, again, energy change is not needed. When we are talking about pressure, all we need is to see the proportion of molecules of gases on each side. So we only need to know the number of gas molecules on each side. That's the information we need. So we need to know their state symbols, we need to know that they're gases, and we need a balanced equation so we know how many are on each side. So the first thing, when you're asking about the effect of pressure, is you just need to add up the total number of gas molecules on each side of the reaction. On the left, we have one molecule of A and one molecule of B, so in total, we have 2 molecules. On the right, we only have one molecule of C, so we only have 1 on the right. Now, remember, this is in a closed system, so the volume is fixed. So I'm just going to add that here. So it's a closed system, therefore has a fixed volume. So, if I was looking at the left-hand side, I've got twice as many molecules on the left as I do on the right. So on the left, I would have a higher pressure because I would have more molecules in a fixed volume. On the right, I've only got one molecule. So on the right, I would have a lower pressure because I'd have fewer molecules in a fixed volume. So we just need to bear that in mind. So if, for example, I'm going to increase the pressure, now, Le Chatelier's principle states that the equilibrium will shift to counteract that change. So if I've increased the pressure, the equilibrium will shift to decrease the pressure. So it's got 2 choices. It can shift forwards to the right, where it would have 1 molecule of gas, or it can shift backwards to the left, where it would now have 2 molecules of gas. Which one of those would be the opposite? Which one would lower the pressure? Well, if I've increased the pressure, it wants to lower it, so favouring the right-hand side would make sense, because then there would be fewer molecules of gas in a fixed volume, so the pressure would decrease. So in this case, the dynamic equilibrium shifts to the right-hand side because there are fewer molecules of gas this reduces the pressure. And the reason is because there are now fewer molecules of gas in a fixed volume. If I was to do the opposite of that, if I was to decrease the pressure, well, if I was to decrease the pressure, Le Chatelier's principle states that it will shift to the oppose that change, it will shift to increase it. So it's got 2 choices. It can shift to the right to produce 1 molecule of gas in a fixed volume, or it can shift to the left to produce 2 molecules of gas in a fixed volume. And I've decreased the pressure, so it wants to increase it, so it will shift to the left because there's more molecules of gas on the left, and that would increase the pressure. So decreasing pressure in this case will shift to the left. because there are more molecules of gas. This will increase the pressure. Because there will be more molecules of gas in a fixed volume. So, the only sort of caveat to this is if you have the same number of molecules of gas on both sides, if we had 2 on both sides, then actually all that means is pressure would have no effect because neither side would be favoured. So pressure only affects equilibriums that have an uneven number of molecules of gas on both sides. So here, this would be affected by pressure because we've got 2 on the left and only 1 on the right. If we were dealing with a system where there was 2 on the left and 2 on the right, then it would make no difference and pressure would not affect that equilibrium system. So, in summary, increasing pressure favours the side with the fewest molecules of gas, decreasing pressure favours the side with the most molecules of gas, and pressure only affects equilibriums with unbalanced numbers of gas molecules. So, increasing pressure favours the side with the fewest molecules of gas, decreasing pressure favours the side with the most molecules of gas. And if you have the same number on both sides, then pressure has no effect. When looking at the effect of temperature on a dynamic equilibrium system, this is when the energy change is important. You need to know the energy change in order to predict the effect of temperature on a dynamic equilibrium. So, firstly, we should know that whatever energy change or enthalpy change they give you is always for the forwards reaction. So, the fact that this is negative tells us that it's exothermic, which means that the forwards reaction is exothermic, which means that the backwards reaction must be endothermic. Now, we should know that an exothermic reaction increases temperature, and an endothermic reaction decreases temperature. So, let's have an example. If I were to increase temperature, then Le Chatelier's principle states that the equilibrium will shift to the left or the right in order to counteract my change. So if I've increased the temperature, the equilibrium will shift to decrease the temperature. And it's got 2 choices. It can go forwards and be exothermic, or it can go backwards and be endothermic. Only one of those will decrease temperature. That's the endothermic reaction. So it will go backwards and favour the left-hand side. So the dynamic equilibrium will shift to favour the left-hand side because the backwards reaction is endothermic. This will reduce the temperature. If I were to do the opposite of that, if I were to decrease the temperature in this case, the dynamic equilibrium will shift to counteract that change. So if I've decreased the temperature, it will want to increase it. It's got two choices. It can go forwards or it can go backwards. In this case, the forwards reaction is exothermic. Exothermic reactions increase temperature. So it will favor the exothermic reaction in order to oppose my change. So in this case, if I were to decrease the temperature of this dynamic equilibrium, it will shift to favor the right-hand side. Because the forward reaction is exothermic. This will increase the temperature, doing the opposite of what I changed. So, in summary, increasing temperature will favor the endothermic reaction, and decreasing temperature will favor the exothermic reaction.